Usually, the staircase paradox is presented through this example where the curve is an actual staircase. We have a diagonal for a square of length 1, which has length the square root of 2, and then we have this staircase curve that at every step has length equal to 2. And then people say this shows that the square root of 2 is equal to 2, which of course is not true. But how do you resolve this paradox is to point out that the limit of the lengths of those staircases is not equal to the length of the limit of the staircases. And in other words, that this length function is not continuous, so we do not have to expect that the length of a limit is the limit of the length. Here's an even simpler example to show the staircase paradox. So we have the interval from 0 to 1, and then a curve that goes h units high, 1 to the right, and then h units down. So the length of the yellow curve is 2h plus 1 in this case. If we divide the interval in 2, and then we go up and then down, but we only go up by h½ units and down by h½ units, then the length of the curve in yellow would be twice 2 times h divided by 2 plus a half. So the length of the curve in yellow, it's still 2h plus 1. We can divide the interval into n parts, and then the length of the curve in yellow will be n times 2 times h divided by n plus 1 divided by n. So the total length is still 2h plus 1. And moreover, the path in yellow as a function of n converges to the interval 0, 1. So the limit as n goes to infinity of those yellow paths go to 0, 1, because as n goes to infinity, every point in the yellow path is closer and closer and closer to a point in the interval 0 to 1. However, the limit of the lengths of yellow paths is 2h plus 1 because every single one of those paths has length 2h plus 1, which is different, of course, from the length of the interval, which is just 1. And by the way, since h was arbitrary, I can make the first limit to be as large as I want it to be, and that difference between 2h plus 1 and 1 as large as I want. So what this means mathematically, from the real analysis point of view, is that the arc length functional, so the functional that sends functions that are continuous from the interval 0, 1 to r2, such that for one of those paths, it returns the arc length of that path, that functional is not continuous. And we do not have continuity because there are, as we have shown, sequences of functions that uniformly converge to some function f. However, the limit as n goes to infinity of the length of those functions is not equal to the length of the limit of those functions.